Like I said, one of the immediate applications that you want to do is to write an ODE that describes a phenomenon, a real-life situation. This is the ultimate goal when you study differential equations, because they are designed to model processes that depend on time. So in the homework you will have questions like this. Write an ODE, an ordinary differential equation, and or its initial conditions that describe the following situation. So let's start with an example. Suppose that the description is the following. Let's say you have a quantity that changes at a rate proportional to the quantity itself, and let's say inversely proportional to the square root of time. So one of the key words to keep in mind is the rate of change, right? I mean, what signifies that the problem is a differential equation problem is that the quantity that you want to model changes at a rate. So that's the key word to keep in mind, because the rate of change, of course, is another name for the first derivative. So it changes at a rate proportional to the quantity itself and inversely proportional to the square root of time. So the first thing to do, of course, is to denote the dependent variable by some letter. Let's say the quantity you're trying to model is a of t. Because the quantity changes with respect to time, that means the quantity itself is a function of t. So this is your dependent variable. And of course, t is the independent variable. And then on one side of the equation, you're going to write the rate of change, because the entire problem is a description of a rate of change. That rate of change may have plus quantities, minus quantities, depending on whether you describe a growth process or a decay process. As you'll see later in this problem, it just gives you a description of the rate of change itself. Now, when you have this quantity proportional to something else, you usually introduce a constant of proportionality, which that may be able to be found from other initial conditions if they are specified. But proportionality means that the rate of change and whatever is described here on the right hand side is going to be proportional via a constant of proportionality. Directly proportional or just proportional means that appears as a factor of k. Inversely proportional means that is proportional to the reciprocal of that quantity. So in this case, it says it's proportional to the quantity itself, so k times a, and inversely proportional to the square root of time, that means square root of t. Now, of course, this will only make sense if t is positive, otherwise it doesn't, right? So you're going to have a bunch of questions like that in the homework. Sometimes you need to provide, as I said, an initial value problem if, let's say, in addition to the statement in the problem here, you have the initial quantity specified. So let's say it says that initially the quantity is 100. Initially is another keyword, means that you know the value of the quantity at time 0. Okay, so a of t is the quantity at time t. A of t is the quantity at time t. So therefore, initially, if you have initially 100, whatever this quantity is, 100 items, then a of 0 is 100. Always, it's important to remember that whatever is initial values, that's not part of the differential equation itself. That's only initial condition, which appears separately from the ODE itself. When you write an initial value problem, the framework is to solve first the ODE completely, if you can, of course, to solve the ODE, and then deal with the initial condition last. Typically that means, you will see later, solving for a constant of integration, because any ODE depends on, any solution of an ODE depends on one or more constants of integration. So in fact, let's actually write an example quickly. Don't worry about how to solve this ODE, we're going to learn that pretty soon. But let's say you have y prime equals t plus y. So this equation actually can be solved later into two. In fact, let's actually take a even much easier example than this. Let's say y prime equals 1 plus y. So that's one of the easiest equation you're going to solve later. In fact, you'll learn a method that will allow you to solve it in a couple of seconds or less. Again, don't worry about it for now how you do this, but the full solution of this equation is just a constant of integration c e to the t minus 1. And in the next video lecture, we're going to go over more examples like this in which we take the solution for granted and then verify that this is indeed the solution of the ODE. So for now, just take this for granted. Although, maybe we can actually verify it at the end of the lecture today to convince yourself that this is indeed the solution of the ODE. But let's say the ODE that I wrote here is attached to an initial condition which says y of 0 equals 7. Right? So we know the ODE, we know the initial condition. Once you solve the ODE completely, which I did already, right? I provided this for you. The very last thing to do all the time is to deal with the initial condition to find this constant of integration. So C is really arbitrary. If I only have an ODE, this is a solution no matter what C is. Again, I'll show you just in a second. But for now, let's see how you do the initial condition. How do you apply it to find C? Well, y of 0 means that you're going to replace t with 0. So y of 0 is c e to the 0 minus 1, and that should be equal to 7. So from the initial condition, you can always find this constant, this arbitrary constant. E to the 0 is 1, and therefore c equals 8. So the full solution of the IVP, of the initial value problem, will be y of t equals 8 e to the t minus 1. Right, so this satisfies both the ODE that I wrote here and its initial condition. And so as the last remark of this lecture, let's actually convince ourselves that indeed this is a solution of the ODE for any C. So how do you actually check that this is indeed the solution? Well, you just plug it into the ODE whenever you see y. Right? So y is replaced by c e to the t minus 1 on the left. So on the left it's y prime, so I'm going to have to take that derivative. And on the right hand side, replace y again with c e to the t minus 1. So when you take the derivative, minus 1 disappears, it's 0. The derivative of c to the t is just c to the t. And on the right hand side, notice that minus 1 cancels. Right? So for any c, this is a solution. And we can provide more sophisticated examples, but I'm going to save that for the next lecture. So in the first lecture, we're going to provide again a couple of examples of ODEs and their solutions. And then finally, we're going to start discussing the very first differential equations that we can actually solve via a generic method. Again, I can't emphasize this enough. We don't have a method to solve any differential equations. We're going to have methods for types of differential equations. So the first types of differential equations we're going to deal with later will be the first order ODE in the form of a description of the derivative. So y prime equals some function of t and y. More generally, a little bit later, we're going to be able to solve, again, the first order ODE in a slightly more general setting. So an ODE written like this, y prime plus a of ty equals b of t. But before we even talk about how to solve either of these, the first focus later on in the next lecture or two is to figure out how we can tell lots of things about the solutions of an ODE without actually solving for it. You can tell a great deal about the properties of solutions without, again, solving for it, which is actually great because most ODEs cannot be solved explicitly. More on that in a subsequent lecture. See you later.